So actually, let me go on and show you those. So here's a derivative matrix. Here's for each of the 3 barycentric coordinates. Okay, and here's some degree elevation matrices. So they're very sparse. Okay, so now the next part of my the next tool I need for this is a way of indexing into multi-indices one index at a time. So if you will, currying the currying the indexing operator. Okay, so take a cubic polynomial here, and you'll have 10 coefficients associated with it if you're on triangles. So C3, 0, 0. So here are all of the tuples, all the multi-indices of order 3. So here are all of the ones that start with 3. Okay, so this is reverse lexicographical ordering. So here are all of the coefficients that start with 2. Here's all of the coefficients with 1 and with 0. Okay, so I've drawn those lines in there. So you can think about indexing this vector not by the multi-index, but by the first index of the multi-index. So we'll write this as C3, C2, C1, and C0. And for example, C1 is given by this vector here. So we can write C alpha as C alpha 1 indexed by alpha prime. Okay, so take the first index and then index by the rest of it. And then C alpha 1 becomes a vector where the indices, that is indexed over a lower dimensional space and a lower degree space. Okay, so now we can use this way of partitioning vectors over multi-indices to partition bilinear forms, or the matrices associated with them. So if you have a bilinear form on the simplex, where one argument is at degree m and one is degree n, so you have a matrix. Just plug in the basis functions and, okay. So now, if you've got this matrix in hand, you can, and you've got polynomials u and v, you can evaluate b of uv just by taking a matrix vector product. Okay, so this is starting to get more familiar to the finite element people here. Okay, so now it turns out you can block this matrix, and you block this matrix by indexing by the first, by alpha 1 and beta 1. Okay, and so as I show examples here. So here are some derivatives where I've drawn in this blocking that you get by partially indexing. So here, this number of columns, there's 10 columns here. So I've drawn in the lines this way. Notice there's 1, 2, 3, 4, just like you would get for cubics. And then it's partitioned, this line should be moved up 1. That's a typo. So it would be 1, 2, 3. So I've partitioned the space of quadratics, if you look at this one. Partition the space of quadratics that way and cubics going that way. Okay? So degree elevation, for 1D quadratics on the cubic, that's what it looks like. And for 2D quadratics, for cubics, you get this way. So notice I've partitioned quadratics along the column space and cubics along the row space. Okay? You can do the same thing for 3D operators, but it takes up more white space on the screen. Okay. Now that I've gone through a crash course in multi-indices and Bernstein polynomials, I can start getting to the heart of algorithms. Okay, so 2 bilinear forms that I'll care about here. You can do the same trick for other forms. You want the mass matrix and the stiffness matrix. Okay, so, and here's the formula for them. Okay, so the mass matrix. Working with Bernstein polynomials, I can write down an exact formula for the mass matrix independent of any numerical quadrature rule. Okay, and so if you just write it down, here's what it looks like. It's kind of messy, but this is a mass matrix of degree m by degree n, so it's possibly rectangular. You get these factorials. Then notice I'm indexing by these multi-indices, so I get those factorials. Then you get the sum of the factorials, and then times this thing here times SD and d factorial. Okay, so there's probably a lot of structure in that. And what I'm going to do next is take away the dependence on the simplex and the dimension just by factoring that out and introducing this new thing so that you recover the element mass matrix by doing this reference mass matrix, if you will, and then multiplying by some extra geometric information. Okay, so now we want to look at this MDMN and ask how quickly can we multiply it onto a vector. Okay, and that will be the heart of our algorithms. But first, let's look at some examples of this. So, I've got everything's a rational number, so I'm turning everything into integers by multiplying by through by a common denominator. So for linears, it looks very familiar if you've done Lagrange polynomials. Quadratics looks a little different. And cubics, here's what it looks like here. Okay. So for 2D, I've drawn in the partitioning lines here. Now, so this just looks like there ought to be all sorts of structure here. Here it is for quadratics and cubics. Okay. So one thing that you should notice here is that on the diagonal, see this 6, 3, 1, 3, 4, 3, 1, 3, 6? There is the 1D mass matrix. Okay, 2, 4, 2, 4. So up to scaling, that's the linear mass matrix. Okay, and up to scaling, that's a constant mass matrix. Same thing for cubics. This 20, 10, 4, 1. There you have it. So up to scaling, these diagonal mass matrices are the mass matrices for one dimension lower. Okay. I'll come back to that in a minute and actually state a theorem about it. So things that we know. These are totally positive operators, which means from linear algebra there'll be a lot of interesting theory that doesn't hold for, say, Lagrange polynomials. They're also symmetric. Turns out there's some other stuff I haven't worked out proofs for, but looks like it's true, at least from the calculations I've done. Okay, so as I said, here's the substructure. So not only are these diagonal blocks 1D mass matrices, it turns out up to scaling, so are the off-diagonal blocks. So if you look at this one here, this turns out to be the 1D quadratic by cubic mass matrix. And if you just plug it in, you verify it with the calculation. Okay, so theorem. This encapsulates those observations I just made. So dimension D, M by N, you look at one block of the matrix. It is the matrix of one dimension lower, possibly updating the degrees of the polynomials. So this gives you a recursion down dimension for the blocks of the mass matrix. Okay? And this holds for D bigger than 1. So for cubics, you can actually reduce the blocks to 2D mass matrices, and so on. Okay? So the second result is actually going to let us relate these blocks to each other. Okay, so this block up a column this way. So notice here, the columns are always running over cubics, but here the rows run over cubics, and here the rows run over quadratics, here the rows run over linears, and here the rows run over constants. So what we will be able to do is actually write down a recurrence that says once we've applied this to a vector, that we'll use the degree elevation operator to write this times the same vector as a sparse matrix acting on that result. So it'll just be a recurrence relation. So this turns out to be true for any bilinear form you like. Okay? So take a bilinear form and plug in m degree polynomials and n degree polynomials. And so that gives you a matrix. If you want the matrix for a lower dimensional space, okay, so restrict, say, the dimension in the first argument, you can write that matrix as the larger matrix times degree elevation. Okay, this is just basic linear algebra. Your sophomores can do this, maybe. But all the mathematics that's required there is basic linear algebra. The same thing is if you restrict in the second argument here, then you get the transpose of the degree elevation operator acting on the slightly larger matrix. And this sets up our recurrence relations. Okay? In particular, you can apply this result to mass matrices. Okay? And that's true for any dimension. So here's the next theorem. You just apply these two previous results. And this allows you to relate the blocks of the mass matrices. So a block where you update one of the indices here is related to just a number. Okay, you have to keep track of it when you prove the theorem, but it's just a number. Then degree elevation times m. So once you've applied this matrix to a vector, this matrix is applied to a vector by a sparse matrix and then scaling the result. Okay, here's an algorithm that encodes that observation here. It's more complicated than just loop over rows, loop over columns, but as I'll show you in a minute, it actually is much more efficient in terms of complexity. So here's the heart of the algorithm. Here is you apply a lower dimensional mass matrix times a hunk of the input vector. Okay? And then you just repeatedly degree elevate that result, scaling it. Okay?